We want to be able to, here in this section, solve a first order linear differential equation. First order means that its highest derivative is 1, so dy over dx. Equation number 1 comes from a bigger equation. It comes from the nth order linear differential equation. But here, the case is let n equal to 1, and so the order, the highest degree, is just 1. I want to be able to solve this. And the method that we use to solve it is actually by the integrating factor. But with this, it's so neat that the method, if we can get it to work right, you don't have to go through the exactness of how we did in the previous section. What I'm saying is you can find the integrating factor, multiply everything by the integrating factor, and then solve using exactness. That was the section 2.4. Or you can use a very shortcut, quick method that's introduced in this section right here. Now, with that being said, if you find the integrating factor for this section and then multiply everything through by the integrating factor, can you solve that using exactness? By all means, yes, you can. That's no problem. You'll get the same result. But with the instructions here, and sometimes instructions seem to be somewhat cumbersome, but I think if you get it, and maybe look at an example that I'll show you, and if it makes sense, then you should be able to do the problem with just ease, you know? That's our goal, to be able to do it. You know, it's like taking candy from a baby. No, that doesn't work. Some of the babies I dealt with, man, you take some, be quiet, man. You gotta give it back to them. I used to work with children's church, man, about 20 years ago. Those kids, man, okay. Boy, they get on me, man. I used to love it. Well, it should be good. But I'm going to show you, and you will understand, in a course like this, that there are things that's introduced that will need to be explained in a way mathematically that all your questions will be answered. In terms of where did this come from. And then the real neat thing is that hopefully tomorrow, Monday, hopefully tomorrow I will give a problem, an application problem, where you can see how a lot of this stuff really fits in to applying something in simple physics, if you will. So we're going to solve this number 1. We rewrite it to look like number 2, and the rewrite is basically he's divided everything by this a sub 1 of x, and so a naught divided by a sub 1 is that p of x, and g of x divided by a sub 1 is the f of x. So I want the equation, the linear equation, the first order differential equation, to look like number 2. If it does, then we have a very simple statement that says the integrating factor is this, period, by looking at this. Give me the integrating factor, and to be honest with you, you're about halfway done with the problem with this short, quick method. Well, the method of solving linear equations, and you saw this in that previous example, that we will force the equation to be exact by finding a linear factor. Here this linear factor is indeed the integrating factor. We denote this linear integrating factor by mu, or mu of x, or just mu. Once you have determined this integrating factor, I don't know why I'm saying linear factor, multiply it on both sides of the differential equation. Find and show that the integrating factor is well defined. Here's what I mean here, that we need to be able to have some type of evidence to what we're doing to show that whatever we're doing here makes sense. I left a blank page to do that. So given the nth order linear differential equation, which is a sub n of x times the nth derivative of y. These are derivatives, not partials. Plus a sub n minus 1, which is these coefficients are functions of x, times the n minus 1 derivative of y with respect x to the n dx, and here this is the n minus 1 derivative, plus, and so on, plus a naught. Well, I better put a sub 1 in there. A sub 1 of x, this is y prime, plus a naught of x times y is equal to g of x. Let n equal to 1. That's what we'll solve for today. Let n equal to 1. This implies that this equation simply becomes a sub 1 of x. That y prime, just say dy over dx, plus a naught of x times y is equal to g of x. Divide through by a sub 1 of x. So this implies that we have dy over dx plus a naught of x over a sub 1 of x times y is equal to g of x over a sub 1 of x. And indeed, this function, or this expression a sub 1 of x, is not the zero function. So here we say let p of x equals this a sub naught of x over a sub 1 of x, and let f of x equals that g of x over a sub 1 of x. Thus, I need to give these equations a name or a number. Tuco said to angel eyes, on the grave there has to be, where the gold is, there has to be a name or a number, you know. So that's equation 1. Let's call this equation 2. Equation. Right here, a naught of x. Yes, sir. I'm sorry. And so thus, dy over dx plus p of x times y is equal to f of x. We call this equation number 3. And so we call equation number 3 the first order linear differential equation. Right? Now, up until this point, we haven't done anything but just rewrite and just say what this is. I want to solve equation number 3. So we solve equation number 3 by determining an appropriate integrating factor. And we called it mu, or mu of x. So what I'm going to do is just claim mu, and then I'm going to multiply everything by mu. So I don't know what mu is, but I'm going to solve for it. It's kind of technically how in the proof of a limit that we say that for the limit exists for all epsilon greater than 0, there exists a delta greater than 0 such that the absolute value of f of x minus L less than epsilon whenever the absolute value of x minus a is less than some delta, and then you go through the proof with these deltas and epsilons. But here's the thing about that. You are assuming something in the proof that you don't even know yet, and that is, what the heck is delta? You know. So when you do that proof, you go through all those steps, and you end up, okay, we can prescribe delta to equal to 1/3 epsilon or whatever it may be. But that's actually what you wanted in the very beginning. Well, here, the way we do this proof of solving equation number 3 is the same way. We assume some integrating factor mu, we apply it to the exactness, and then from that, we're able to actually solve for it. Once we solve for it, because I've had questions years ago in DE, you know, when I wouldn't go through these steps, and they would say, why is mu equal to e to the integral of px dx? Well, I want to show you why. So when I get through showing you, there's no more questions. Well, guys, it never works with your wife at home when you want to prove her something mathematically. It would be good. Let me show you this mathematically, dear. You know. Because look, the mathematical proof, it answers all questions, folks. I mean, when you're done with it, there is nothing else that we can do but just go and have a party, you know? Doesn't work with my wife, though. 20 years. But anyway. She was like, what? Okay, dear. But anyway, so here is equation number 3. It's this dx over dy. This was plus p of x times y equal to some f of x. The first thing I want to do is write it in the form of m dx plus n dy equal to 0. We're used to seeing that from section 2.4. So multiply everything through by dx. So I get dy plus p of x y dx is equal to f of x dx. So I'm going to write it in that form. So what that is for me here is p of x y. I'm going to get this. So I need the dy over there. I'm going to subtract this f of x dx on both sides. and plus dy equal to 0. Now notice that m is equal to p of xy minus f of x. And n is equal to 1. Are you with me there? Do you see that? Just thinking about the exact, equation. And where I have m dx plus n dy equal to 0. I look at m, I look at n. Now, just based on what I have, if I take the partial of m with respect to y, this gives me p of x, and the partial of n with respect to x obviously is not going to give us p of x, it gives us 0. So this is not exact. So we will force the equation to be exact by multiplying through by the integrating factor mu. Let's call this equation 4 here. So we will force 4. We will force the equation. This is to be exact. By multiplying through by integrating factor called mu. So what I have is I have this mu of x times this p of x y minus f of x dx plus mu of x dy is equal to 0. So now I check here the partial of m with respect to y. So this whole side right here is m, and just that mu of x is n. So I take the partial of m with respect to y, where everything associated or multiplied to the y becomes the coefficient. So I take the derivative here of y, that's just 1 times its coefficient. So here, this is just mu of x times p of x. And the partial of n with respect to x, well here mu is a function of x, so this is just d mu divided by dx. Well, to force exactness, we say that here these partials must equal. Right? So to be exact, the partial of m with respect to y must equal the partial of n with respect to x. That implies that mu of x times p of x must equal to d mu over dx. Sounds like some country talk down in Orville to me. Go get d mu and put it in the shed. But anyway, it's bad. Oh boy. So what I have here is an equation that must be solved. Why it must be solved? Because I actually want to know what is mu. What does mu equal to? So I'm going to solve this, what I have in boxed, solving for mu. Notice that we can separate the variables. I have a mu here, I have a d mu over there. I have a p of x, I have a dx right there. So multiply both sides by dx, divide both sides by mu, right? So here, solving by separation of variables, we end up with, let's see, I have P of x dx is equal to 1 over, I'm just going to say mu, and this is times d mu. Variables are separated. I integrate with respect to the differential. So here I integrate P of x dx, that's equal to the integral of 1 over mu d mu. Space is running out downstairs. So this implies that I don't know what the integral of P of x dx is. And I have learned through time that if I don't know what something is, I just let it be. I don't try to make up anything. Right? Hey, Mark. So I don't make up anything. I just let it be. The integral of P of x dx is the integral of P of x dx. What's the integral of 1 over mu d mu? That's right, the natural log of mu. You got it. So this is the natural log of the absolute value of mu plus some constant c sub 1. And so here I have, if I can just write this first, the natural log of the absolute value of mu plus c sub 1 is equal to the integral P of x dx. Add a page. Just rewrite that here. This is the natural log of the absolute value of mu plus c sub 1 is equal to the integral of P of x dx. Let's here take mu to be on the interval, the interval from 0 to positive infinity. That implies that I can drop the absolute value sign. So this is the natural log of mu plus c sub 1 is equal to the integral of P of x dx. Well, you recall back at those separable variable equations, once we integrate it, typically we could exponentiate both sides. So we want to get rid of that natural log. So we take here e to the natural log of mu plus c sub 1. Here is equal to e to the integral of P of x dx. So can't we write this as this e to the c sub 1 as c times here this e to the natural log of mu is equal to e to the integral of P of x dx, comma, where c is equal to e to the c sub 1. And I was well pleased when I read in the book the author, he has jokes too. He said, let c equal to 1 and that simplifies life. I thought that was a good statement. It's in the textbook. I said, man, he's funny. Well, you got to appreciate math to be able to get that. That won't work on the comedy stage. Anyway, so let c equal to 1. And here, this implies that mu, e to the natural log of mu is just mu, right? So this is mu is equal to e to the integral of p of x dx. So mu, or mu of x, is equal to that. That becomes our integrating factor. Okay? Now, we went around the world to get it, but we got it. Now, once you go around the world and get it, don't go around the world no more. Right? Just stay right here in Tanner, Alabama, and just say, okay, mu is this, and you tell your friends, don't ask me where it came from, because you got to go back to this whole proof, right? Well, since I have mu, we can look at now the steps to solving this differential equation. The function mu of x is e to the integral of p of x dx. This is called the integrating factor. Now here's the method that we solve, and I work maybe a couple of problems here with this method, and then we'll go home. What I'm going to do is to make sure that I write the equation in the form of dy over dx plus p of x times y is equal to dx. That's what we're saying here in the first step. Remember to put a linear equation in the standard form, and that is dy over dx plus p of x times y is equal to f of x. I'm going to write it in this form. The reason why you're doing that is that you can identify p of x. So you can write mu equal to e to the integral of that p of x dx. That's why you want to write it in that form. That's the only reason. Once you do that, here's a good part. And once you do that, you multiply everything by the integrating factor. The left side is already, since that's the integrating factor, the left side is already the product of the derivative of the integrating factor and the dependent variable, which typically is y. Just write that. It's equal to the right side, which is the integrating factor times that f of x. And after that, integrate both sides. Integrate both sides, you get the answer. Let me show you what I'm talking about. Here, this is the part where we get to the baby, and I want to take the candy. Give me that, when the mama's not looking, give me that piece of candy. Man, you messing up everything. And then she says, how's everything going? Everything is fine, dear. Everything is fine. Look at you. Man, my kids to whip my tail, man. They were rough, man. I used to be sweating, boy. Is everything okay? Yeah, everything's fine, baby. Praise the Lord for women, right? But, oh, man. So I'm going to write this in the form, very simple problem. I'm going to write it in the form dy over dx plus p of x times y is equal to f of x. Now, how do we get p of x before? We just divided everything through by whatever was multiplied to that derivative. So divide everything through by the 3. And can I write just y prime instead of dy over dx? Is that okay? Just write y prime. It just saves us. So this is y prime plus 12 divided by 3 is 4 times y is equal to 4/3. Okay. So according to our work that we just got through doing, our mu is equal to e to the integral of p of x. P of x is just 4 times dx. Well, that gives us, when I integrate that, that's just e to the 4x. So that's my mu. So once I get mu, I'm going to multiply this equation, everything here, by that integrating factor, e to the 4x. So what I get here is e to the 4x times y prime plus 4 times e to the 4x times y is equal to 4/3 times e to the 4x. Now, the good thing about all we've done is that you force something to be, and so this is like all the pieces of the puzzle all spread out. So now the next step is just to take one statement and say, look, This is what that is. This is really the product of the derivative of e to the 4x and y. It's the product derivative, right? So what is that? This is the product of the derivative with respect to x of the integrating factor e to the 4x times the dependent variable, which y depends on x, so it's y. That's what the left side is. That's equal to what I have on the right side, 4/3 times e to the 4x. So in other words, look, this left side is already the result of the product, the derivative of the product of e to the 4x times y. If I apply the product rule on this, it's the derivative of the first, which is 4 times e to the 4x, right here, times y. That's that. Then it's plus now the derivative, it's the first times the derivative of the second. That becomes e to the 4x times the derivative of y, which is y prime. See that? So there's no work now on the left side. We're going to work on the right side. Now integrate both sides. Integrate both sides. So it's the integral of that derivative with respect to x of e to the 4x times y dx is equal to 4/3 times the integral of e to the 4x dx. The integral of a derivative, according to the fundamental theorem of calculus, part 2, says that the integral of the derivative, likewise, the derivative of the integral is just the function. Right? The function here is just e to the 4x times y. So the integral and the derivative are inverses of each other, just like the natural log in the e base. So all I have left here is e to the 4x times y. No work over there. Right? So this is e to the 4x times y is equal to integrate the right side. That's 4/3 out in the front automatically. This integral of e to the 4x, I have to let u equal to 4x. So du picks up 4 dx, so it's a 1/4 in there. So 1/4 times 4/3 is just 1/3 times e to the 4x plus the constant. Divide everything through by the e to the 4x. So this is y is equal to 1/3 plus c times e to the negative 4x. That's the answer. Now, in Webassine, they're going to ask the question, is this problem transient? And if it is, what's the interval by which it's said to be transient? Transient simply means that if you let x go to infinity, does the solution part go to 0? And the only part that would go to 0 if you let x go to infinity would be this c over e to the 4x. That goes to, this guy would go to 0. So we say that the transient part is this, and then it asks for the interval by which it exists on. So we note that, and I'll talk some more about it on the day we come back. But here, the transient form of this problem is c times e to the negative 4x. And here the interval by which the solution exists basically is talking about continuity or discontinuity. Notice here for this problem, x could be any real number, and you'll still get a solution for y. Right? X can equal to 0, and so c divided by e to the 0 is c divided by 1. X can be negative, positive, rational, irrational, doesn't matter. So here the interval It's from negative infinity to positive infinity. And so I'll state more about that and give that definition for the so-called transient. I don't know why, but in Web of Science, he asked, almost every problem, is it transient or not? And if it is, state the interval by which it is transient. Well, I just was able to work just that simple problem. I'll work some more. You try your hands at that. That method here for this problem is applied to every problem in this section. It's very straightforward. Thank you.